I don't think the UAV can keep this up for long. The battery can't take these kinds of loads. In a world where UAVs are redefining logistics and defense with limited range and payload capacity, we asked, how can we exceed these limits? Meet Team 25039, the hybrid electric demonstration engine for a heavy lift UAV.
Current unmanned aerial vehicles, known as UAVs, face limitations in range and payload capacity due to battery energy density. This project addresses this challenge by designing a scalable hybrid electric system combining a combustion engine with electric propulsion to achieve the power-to-weight ratio required for cargo missions. The powertrain, though not flyable, is simulated using MATLAB Simulink to evaluate performance under flight conditions. The system is designed to scale to a UAV with a 2,200-pound gross takeoff weight, including a 100-pound payload capacity with a 2-hour runtime. The project consists of two main deliverables, a tabletop powertrain and a Simulink simulation. The tabletop features a hybrid electric powertrain with real-time diagnostics monitored by a complex data acquisition system. The simulation allows for customizable powertrain configurations and performance analysis over various flight profiles. This proof-of-concept design validates the feasibility of hybrid electric systems for heavy-lift UAVs, paving the way for future development.
Hybrid electric heavy lift UAVs open the door to life-saving applications and revolutionary capabilities, like fire relief, search and rescue operations, agricultural uses, delivering aid to disaster zones, transporting cargo, and so much more. Our proof-of-concept powertrain and Simulink simulation were developed with all of these instances in mind.
As for our system's powertrain, we approach the integration of each component having scalability and modularity in mind. Every component from the clutch coupling to the converter racks were chosen while factoring in hazards associated with temperature, achieving maximum efficiency and reliability. We ran a series of trade studies to evaluate alternate configurations to ensure that our final design would meet key engineering standards. The standards we abided by focused specifically on four main components: safety, consistency, efficiency, and interchangeability. While the physical system was built throughout the duration of our project's timeline, we also built the simulation in parallel, which ensured that our model aligned with real-world expectations.
Now I'll walk you through the power distribution system of our hybrid electric engine. First, we have our internal combustion engine that transmits power into our generator and converts that into electrical power. We then have the bridge rectifier that converts that AC voltage into DC voltage. That then flows down through our capacitor bank, which ensures that the downstream electronics have stable voltage and limited ripple voltages. That then connects to our circuit breaker, which acts as a protection measurement for our downstream electronics. We also have our first set of bus bars here, which is connected to our DC step-down converters. The step-down converters will step down the DC voltage coming from our engine to our nominal voltage of 44.4 volts. And again, we have another set of bus bars here, which is connected to the shunt resistor. The shunt resistor will measure the power output from our mechanical side and transmits that data to our lab jack, where it will monitor in real time. From the shunt resistor, we go into our central power distribution hub, which acts as the central hub for both our mechanical power and our electrical power. I also do want to notate that we do have our common ground reference as our copper grounding bar here for our entire system. Now I'll go ahead and walk you through the battery down to the central power distribution system. The battery is connected to our discharge relay and then again connected to another set of bus bars. The DC step-up converters steps the 12 voltage from the battery to our nominal voltage of 44.4. That then is connected again to another set of bus bars and then to another shunt resistor, which measures the total power output of our battery. And in our central power distribution hub, we have connected the electronic speed controller, which drives the motor based on our total power output. Now, with the recharging circuit, we do have a solid state relay and a DC step-down converter that recharges our battery in our system. All of these components here make up the system of our power distribution system.
Moving on to our simulation, we'll start with the engine portion. This is where the user will either specify the level of throttle at each time interval or run the calibration mode. The calibration mode will take the selected simulation runtime and step up the throttle incrementally until a max throttle is reached at the end of the run. This is an excellent tool to assist in finding the throttle required to meet the desired RPM. The engine side consists of an engine model connected to a logic-based clutch, and then to our generator itself. The DC side allows for monitoring of both the inverted voltage and the buck converter controlled voltage. Connected to the buck converter output is the switches to the battery. The battery is connected to a boost converter with a user-specified output and activated as part of the hybrid function. Using the desired RPM and ensuring the battery is at a sufficient charge, the switch engages, allowing the boost converter to output the desired voltage. Finally, the buck converter output is rectified back to AC for use in our motor with its own power measuring system and RL and LC filter to match the ESC demand. Our Simulink model captures real-world system dynamics. The flexibility of the model makes it a powerful tool for future designs.
The data acquisition, or DAC subsystem, is the bridge between our hardware and our software. It allows us to monitor any physical tests such that the results can be compared to the simulation. The DAC subsystem is critical for ensuring accuracy, showing that the simulation corresponds to physical phenomena and isn't abstract. The DAC subsystem is almost entirely run through a single component, a LabJack T7. This device can send and receive variable voltages through an array of channels, though only 4 are relevant for this project, excluding the grounds. The LabJack is used to gather current and voltage data from both the internal combustion and battery sides of the power distribution system. This allows for generated power to be calculated, which is a major deliverable for this project. To ensure our powertrain is safe even when handling large currents, the DAC system has an emergency shutoff functionality. By sending a periodic signal to the electronic speed controller, the DAC can cause a shutdown of the powertrain propeller in less than 1 second.
In an effort to keep safety as a priority, a couple of our requirements were not able to be verified. These included our system runtime of 2 hours, power output of 5 kilowatts, and operating temperature of less than 180 degrees Fahrenheit for the generator and internal combustion engine. These requirements could not be verified due to safety concerns regarding the clutch coupling system, as well as sponsored advisement. Although we weren't able to verify all of our system requirements, the requirements that we verified are the following. Through our simulation, we were able to produce a thrust-to-weight ratio of 6.58, which is much higher than the requirement of 1.83. We were able to find our fuel efficiency for our engine to be 0.198 gallons per hour, which is well below our requirement of 0.6 gallons per hour. We were able to receive a shutdown command from our LabJack to our system in 0.76 seconds, which is below the requirement of 2 seconds, verifying all our DAC requirements. Finally, our system was able to operate between the ambient temperature of 40 to 120 degrees Fahrenheit, verifying another requirement. For our simulation, our simulated power output was within 7% of our predicted power output of 5.2 kilowatts. Even though there were key requirements that were not met by our physical powertrain, our simulated powertrain proved to be a success.
Our hybrid electric powertrain is not just a project. It's only the beginning of what's possible, a stepping stone towards smarter, safer, and more sustainable unmanned aviation. We'd like to thank Tacticum and Noble for sponsoring this project, as well as our mentor, Carrie Jones. Thank you for watching. We can't wait to see you on Design Day.